All right, hi everybody. Welcome back to week 2 recitation for Maine. What is it, 4070? Hope your first week in this COVID semester wasn't absolutely terrible, and that online classes are going well. So, just a bit of housekeeping. Today is the 10th of September. There's a homework due today. Originally, I had posted that the due date was the beginning of class time. I have since changed that to end of day today, and moving forward, all of the homeworks are going to be due at the end of the day as opposed to start of class time, just to make things a little bit easier for you guys. And in general, you should expect a homework due every Thursday moving forward, barring exam weeks. Just trying to keep the pace of our homeworks um, on par with where they've been in previous years. And with that, homework 2 is posted and is due a week from today. So, getting right into it, what did we learn this? We learned a few, or this week. So we learned a few different things, and personally, I like this week in aerodynamics because it's just maybe a handful of equations that you really need to hammer home and get comfortable with using. So the first of that being the Kutta-Joukowski, I think that's how you pronounce it, theory of lift. So a lot of people, Jesus, that's terrible. A lot of high school physics classroom, wow, sorry, airfoil's not looking good today. It's been a long day. A lot of high school physics classes teach you a basic and false idea that lift over an airfoil is generated by the principle of fast moving air on top and slow moving air on bottom, slow being of a higher pressure than fast due to Bernoulli's, and then you generate lift due to the principle of equal transit time from the leading edge to the trailing edge of the airfoil. This is bad. We don't like this explanation. It's not good. It's wrong. So what Kutta-Joukowski tell us is that it's actually a function of the circulation imparted in the flow by the airfoil. So, whoops, that's not it. Lift is going to be equal to the circulation times the density times the velocity of the flow. So lift, this is a 2D lift. And I guess that naturally leads us into what is circulation. Circulation is the rotation of fluid. How do we define that? A couple different ways. So circulation, specifically 2 different ways, is the contour of, not just ds, of velocity over some contour of integration. And another definition that I probably prefer, double derivative across the surface of the curl of the velocity. So both of these definitions are quite useful, and you will see both of them in the upcoming homework too. I'll talk about that in a little bit. I personally prefer this one for a lot of applications just because I have a pretty good understanding of vorticity. So what this is the projection of the vorticity vector in the direction normal to the surface enclosed by your contour. It's basically, how much vorticity exists within this region of interest. And so then, again, that is going to then naturally lead into what is vorticity. Vorticity is defined by the curl of the velocity, which you should know from linear algebra, IEA, I forget where I was first taught this, is going to be equal to this. So I tend to not actually memorize the result of this equation. I think it's nice to be able to fully work this out for yourself. You have to do it a few different times for homework, and I'm assuming this will be an exam problem eventually. Okay, so this being your vorticity being twice the angular velocity of the flow. Sometimes that's written as W. Depending on the textbook, these actually switch sometimes. It's kind of annoying, but this is angular velocity, and it is twice your, other way around. Vorticity is twice your angular velocity. And an important idea that will come up in this week's topics is the idea of irrotational flow. If a flow is irrotational, you should immediately ding in your head that the vorticity equals 0. So whenever you hear that, you should have this idea. Irrotationality. Curl of velocity is 0. Okay, so the next thing we introduce is the idea of the stream function. Before you can even really think about the stream function, you have to verify that it's even possible to derive a stream function. And the way you do that is to check if it is compressible. If a fluid is compressible, then stream function doesn't work. Just don't even think about it. But how do we check compressibility? We take the gradient of velocity vector and set it equal to 0. This is the incompressible steady state continuity equation for Navier-Stokes. And this equals, pretty basic, du dx plus dv dy. So whenever you're given a problem and it says, generally stream functions problems start with the idea of, is it possible to generate a stream function? You have to check this. And then once you check that and verify that yes, it's incompressible, or no, it's not, well, the problem's over. Once you verify that it is possible, you can then solve for the stream function by this equation. U equals d phi dy, and v equals d phi dx negative. It's also important to know that the stream function is a two-dimensional concept. So if you have a planar flow, it has to be a planar flow in order for a stream function to exist. I don't think you're going to be needing to solve for that. But once you get this, it's just a matter of separating and integrating these two equations into something that is hopefully reconcilable if everything is correct. So it's just a matter of integrating u with respect to y, integrating d phi, and then over here, we have the same thing, integrating v with respect to x equals the negative integral of d phi. Hopefully you get something. For example, I'm just going to make something up. You get phi1 is x squared plus y plus c x squared plus some function of y. You don't actually know what it is, plus c, and then you get your other stream function is 3 over 2 y to the 5th plus some function of x plus c. This is a reconcilable set of equations. So you can have this function of x makes sense here, this function of y makes sense here, and your c's are arbitrary. So then your stream function becomes x squared plus 3 over 2 y to the 5th plus c. And also you'll sometimes get these in cylindrical coordinates. So this is Cartesian and cylindrical. What are they? VR is 1 over r d theta, and v theta is negative. Maybe. Yep, that's correct. So again, same idea here. It's just an integration problem, and you have to reconcile it. All right, so the next thing that you guys learned is the idea of the velocity potential function. Here it is, or here the major thing that you have to be looking out for is rotationality of the flow. If there's rotation in the flow, then you can't reconcile. The equations don't work, they don't reconcile, and there is no velocity potential function. So immediately off the bat, if you're asked to find the velocity potential, you have to check, is it irrotational? So again, talked about this before. Is the curl of velocity 0? You have to check that. If it isn't, then immediately you know that the velocity potential does not exist. But once you decide that it is irrotational, velocity potential is defined as v is the gradient of phi. So we know v is the phi dx, and v is d phi dy. Cylindrical coordinates again. So same idea, it's an integration problem that you then want to hopefully reconcile. If you can't reconcile it, then there's something going on. You gotta either double check this or you've made a mistake here. And one other point there is to know about the stream function and velocity potential is that they're always orthogonal to each other in the flow. You may at some point be asked to draw them for a certain flow. Could be, a source flow, a sink flow, something like that, a vortex. And it's always helpful to, once you know one, it's pretty quick to be able to roughly draw the other one because it's always orthogonal to each other. And then the last thing that we were talking about this week, or started talking about this week, is the idea of the Bernoulli's equation, which I don't think we finished, but we probably will finish this Monday. It's something that you guys should have seen before. It's the idea that the static pressure plus the dynamic pressure, that's ugly, is going to be constant along a streamline. And if the flow is irrotational, which is an assumption you can make in a lot of problems, this is true everywhere, not just along a singular streamline. So with this, you can do a lot of fun things. You can couple it with the continuity or conservation of mass equation and get a few useful figures. So one thing we talked about or discussed in the notes is this. If it's incompressible, drop this, drop the rows. You can get a term for V1. This equation coupled with this equation is fairly useful. It's used in a number of applications and is discussed in the homework problems. I think you guys should have some experience with these, and they shouldn't be too bad for your homeworks. And one application that is common to talk about is a pedostatic tube, which is a tool used for determining airspeed of an aircraft. So a pedostatic tube kind of looks like this weird little L-shaped thing. It's got a hole, two holes. That go into two pressure gauges. Wow, that looks absolutely horrific. Yeah, I'm just gonna erase that. All right, so pedostatic tubes point directly into the flow. So there are two pressure ports, one pressure port facing the flow and one pressure port orthogonal to the flow. So this is going to take your total pressure, and then this is going to take your stagnation pressure. So there's two interesting things going on here. So if I'm going to call this 2 and this 1, if we plug this, we bring over our friend Bernoulli, P1 plus 1/2 rho V1 squared. Here, V1 is actually just going to be our V infinity term, which is what we're trying to solve in the using a pedostatic tube. We're trying to find out how fast we're going. And here on our static pressure side, there is actually no flow. So all the flow is orthogonal. So the only thing you get is the static pressure pushing inward. There's no pressure being generated from the actual velocity of the flow itself. So we can drop this term. So the pedostatic tube works by taking measurements. It's going to separate these two pressure, and it's going to give you a number for P2, and it's going to give you a number for P1. So rearranging this equation, we can solve directly for our V infinity velocity being P2 minus P1, 2 over, what is it, over rho? Yeah, over rho. And then, yeah, this is the general idea of how a pedostatic tube works. You can see these little guys poking out of a lot of different aircraft, and they've been important for a while, I believe. Okay, so moving forward, let's briefly discuss homework number 2. So it's a 6-question assignment. Number 1, what am I asking you for? I am looking for you to use Stokes' theorem to calculate the circulation in some rectangular geometry given a flow field. With this, I'm simply looking for the application of this idea. It's a fairly simple geometry. I hope you guys don't have too much trouble with it, but you can always reach me via email or Skype me during my office hours, and I'm happy to help you through it. All right, problem number 2, likewise, is an application of something that I think you guys should have a good handle on. I'm asking for you to determine if a flow is irrotational and incompressible. So that's just a matter of checking the 2 equations we previously discussed. Let's see. Scrolling through it now. Number 3, I think you should have a good handle on. Number 3B might be kind of tricky, but I give you a pretty useful hint for the geometry. It's tricky if you haven't seen anything like this before. Again, you're searching for circulation, and I give you a hint that's fairly useful. That's make the substitution that ds is actually a double integral of dr d theta, or sorry, r dr d theta. So then the equation becomes the double integral of vorticity, r dr d theta. And with the given flow field, that should simplify things and hopefully make sense to you. You should be able to reach the solution there. 4 is just another vorticity problem. I'm not going to get too much into that. 5 and 6 are both Bernoulli. I hope that's how you spell it. Both Bernoulli applications. It's basically just asking you to reorganize them, solve for certain things. I think number 5 is a MATLAB question, or Excel, however you want to do it. It shouldn't be too bad. Oh, and for homework 1, I kind of apologize. I think some people had some issues copying and pasting the data that I provided in the table. I'll try to correct that issue moving forward, but for now, you don't have any data. It's just a matter of plotting some equations for this homework. And with that, I think that's all I have for you. Have a good week.